Okay, I'm just having some issues here getting my image. Let me see if I can do this. Okay, that works. Right. Okay, that's cool. I'm just inviting some people at the moment. Great, thanks for Frank. I'm going to invite people in. If you want to be invited, give me your Google Hangout address, or rather your, what do you call it, Gmail account. I want to get started because I've only got about 29 minutes. Sorry for the boring beginning, everyone. It is what it is. Trying to invite Matthew because I know he's about at this time. Okay, if anyone wants to join on their Gmail account, they need to find some way to send me their Gmail account, and then they can ask questions. You can also then ask in the group chat as well, questions without being seen, as it were. Okay, I now have about 26 minutes before I need to go. So I'm going to open this very, very soon. Okay, and welcome to anyone that's watching. In fact, I'll probably start this proper when we've got about 10 people. I'll try and get someone in for asking questions. Matthew, if you're watching, can you accept the invite? Okay, if people want to ask questions on Skype, then they can do that. I'll try and keep a track of that, but it's going to be quite tight now. Okay, so welcome to this. We've got 10 viewers, or we had 10 viewers. I am about to jump on a bus to go to Vienna. My videographer, Emmanuel Ruggiero, was shooting a commercial, so he was unable to video some of the material that I wanted to get out before I traveled to Denmark. The reason I want to get this out is so that it cannot be captured. And presentation material prepared. Beyond this YouTube recording, I will put the links to the relevant documents. Essentially, there's a couple of things I want to talk about. One is it's all related. And it's kind of the material that was going to go into the second presentation, but I want to get it out there right now. So essentially, we're going to do a couple of things in the coming months. One is, as you well know, that we've sourced some nickel-62, and we are going to run some experiments, probably in California first, using the nickel-62 to see if that promotes the effect. More interestingly, though, there's a lot of debate about what's going on in the process, quite rightly so, and this is a debate that's been going on for over a quarter of a century. However, there are a number of leading theories, and we would like to try and see if we can understand whether one theory is correct or not. So I was trying to find out some way to do some in situ isotopic tracing of the reaction. And there's two leading theories by people that claim to have successfully created excess heat and transmutations. And there are a lot of researchers that are operating on the basis that one or other of these theories is correct. One of them is the ultra-slow neutron theory by Robert Goddess at Berlin. And the other one that we hope to be able to test in this is that of Francesco Piantelli, and that is the capture of the proton. That's H-, that's a proton with 2 electrons. Anyway, if there are slow neutrons, we want to be able to see if that does something, and if there are H-, rather protons ejected, we want to see if that does anything. So I was trying to find something that to sit in the cell, not really change its chemistry that much to what most people have been doing in their research, and is very well understood and would give us a signal that was very clear should one or other of these effects be occurring. And it just so happens that there is a process called positron emission tomography. This is used in cancer research and in diagnosing cancers. And it's because there is a sugar-like molecule that uses a isotopic tracer that is more absorbed by cancerous cells than non-cancerous cells. What this is you're using 18 oxygen. This is an isotope of oxygen which is heavier than the other stable isotopes and is only in standard water at very low concentrations. And what people do is that they put this into a cyclotron, they expose it to high energy protons, and this does a proton-neutron knockout reaction, and the 18 oxygen goes to 18 fluorine, and this is then injected in this sugar-like molecule into the body, and it does as I previously mentioned. What happens is that the oxygen that has been transmuted into 18 fluorine decays back to 18 oxygen with a positron. This an electron, and it annihilates, and it produces 2 opposite flying gamma of 511 keV. And why I really got onto how this is interesting is because 511 keV, we can observe this from outside of our cell. And by taking 18 oxygen and putting that into an aluminium oxide molecule, so you have Al2-18O3, we can introduce something into the cell which is already in our experiment. Therefore, we're not adding anything we don't already have. And the idea is that if a proton, so-called protons ejected by interact with the 18 oxygen in the aluminium 18 oxide, we will see these 511 keV photons coming out. The beauty about 18 oxygen and 18 fluorine is that, as I said before, a huge amount of research. I mean, it's just an incredible amount of research done into this. So it's very, very well characterized. And so you can know the activation energy, the energy which you need to have your protons. I can look that up for you in a sec, but essentially, if I'm going to switch screens here and just show you what the outcome is, you have a 100 and, is it going to do it for me? Oh no. Do that, but it's not doing it. It's not switching cameras. Okay, give me a second. Oh no. Have I gone? Oh no. Okay. You'll have to trust me on this. I had a lot of slides prepared, and Google's not allowing me to show them. I don't know why that is. No, it's not allowing me to show them. Okay, so I will fire off a lot of different links. Have I frozen? Oh no, this is not good. Okay. Okay, I'm back in the room. How can I do this on? Maybe Google Hangout will let me do it. Can I share a window? Program window. How ridiculous is that? Oh, I know what I can do. Sorry, this is not how I wanted it. You must appreciate that. I can do Minicam. I can do. Okay, this is going to be very awkward. Okay, let's see if I can do this. Sorry. Okay, this is the best I can do, I think. I know what I can do. I can do this. So I'm just wanting to show you some images, and okay, this one. Okay, let me show you this. This might work. Sorry. Okay, have we got it there? Oh no, it's not going to show it. Oh. Okay, we can probably do it like this. Okay, all right. This is just totally not ideal. Okay. This is not ideal. Thanks for sticking with me. I've got about 10 minutes. Okay. So I don't know if you can see that, but you've got some 18 fluorine there of 1.829 hours, which is 109 minutes approximately. And you've got the decay energy there. Actually, it's free, but it's a positron emission, which will create these very distinct emissions that we will be able to observe. And it's 100% yield. And it goes back to 18 oxygen, which can then go back into the cycle. Now, that is, there's some very specific things about this, and you can go and do the research. It was in the presentation that I wanted to make, but essentially, it's been very well studied. You look at the energies that are optimal for creating 18 fluorine from 18 oxygen. It's around about 5.1, 5.2 mega electron volts. So if you consider that, I mean, that you get 6.7 up to 6.7 mega electron volt protons, then and also the research suggests that you don't really get any yield of 18 fluorine if the protons are below 4 mega electron volts, although the threshold is lower than that. You can say that the protons are above 4 mega electron volts if we're observing this photons from the experiments. And so we acquired some aluminium 18 oxygen from a Russian supplier. It cost about, I think, $800 and $900 or something, including delivery for 1 gram. And we can show you pictures of that in due course. But the beauty of this is, so if we're getting the protons, we should observe this. And to a certain degree, is some sort of feeling that there was, this may explain why Focardi wanted to look for the positron annihilation. And there are reasons for that. Anyway, about neutron detection, ultra-slow neutrons, I'm not so sure this will occur in terms of the proximity of the aluminium 18 oxygen is not lattice. That's not important for the proton ejection, but I think it might be more important for the ultra-slow neutrons. The study of ultra-slow neutrons is not anywhere near that for positron emission tomography. Anyway, this is the 19 oxygen decay. Obviously, you can see it's an incredibly fast decay by comparison. 20. Hold on, I don't even know if people are seeing this. Okay, is everyone seeing that? To everyone. So what I was talking about here was the 18 fluorine, 1.8 hours, which is 109 minutes, and the energy is 633 on the positron, and then you get the positron electron annihilation. In the 19 oxygen, you've got a 4.8 mega electron volt beta minus, which will give you a very different signal. And so for the neutron interaction with 18 oxygen. So proton-neutron knockout creates 18 fluorine. Neutron would create 19 oxygen. We're not so sure that this particular reaction would occur. But the idea is that we end up with knowing if Piantelli is right or not, or if Brillouin, or if there's a bit of both going on. So that is that. Okay, so that's one experiment we're going to be doing, and there are 3 people that have the capability to do that right now. That is Bob Higgins, Matthew Vallat in France, Bob Higgins in US, and also Alan Goldwater. So it's a bit of a race to see who. They all have some aluminium 18 oxygen. I think part of this presentation for people, maybe something else that was in the second presentation that I wanted to get out of the door before I hop on this bus to go to Aarhus. And that is about how I see successes in these different successful replications and researchers. The first aspect of that is, I'm just going to stop the sharing here. The first aspect of that is the use of low work function metals. And essentially, if you go and look at what Iraj Pajhamazad did with his zeolites, zeolite is an aluminosilicate, which contains sodium, potassium, calcium, and barium. So you've got various salts or whatever of those alkaline metals in the zeolite. Celani in 1994, he was doing some analysis, having had some successful results using some garage-bought deionized water. He couldn't understand why it was, and he discovered that it had calcium ions in there, and he discovered that it seemed to be promoting the promoted the effect in electrical cells. And so he did a study of various other low work function materials and found that barium was the best, but also strontium was a good compromise. So he used barium in his electrolytic cells, and currently in his treated wires, he adds strontium to them. In about 2000, Iramura of the Mitsubishi fame, and this is a transmutation by gas permeation, says he thinks it's by himself, but maybe with his colleagues, from theoretical considerations, discovered that low work function metals were a key ingredient to get transmutations in his system. And what he uses is calcium oxide. So this is calcium oxide, which calcium is also present in the zeolites of Iraj. And then we look at Piantelli, and this is not public knowledge, but it will be right now. his cells outside of his nickel rod, he had a Maycore structure supporting the stimulation and the we call it the heater element. And Maycore contains magnesium oxide, aluminium oxide, potassium oxide, boron trioxide. So we've got potassium oxide in there. So much later on in 2015, in his new patent update, he recommended cesium. Rossi is said to have used potassium oxide in his low temperature ECATs. When you look at these things, and you can go and look on Wikipedia for the different work functions, but essentially Celani's barium has 2.5 to 2.7. One now is 2.59, so it's somewhere in the range between barium's work function. But if you look at potassium, for instance, it has a work function of 2.29. Calcium has a 2.87, and cesium has 2.1. Okay. And essentially what work function does is it's its ability to essentially donate an electron. And it kind of, if you look at what work function is on Wikipedia, and maybe I can pull that up for you. Have we got it here? Right, I've got about 6 minutes, and I want to get to the real crunch of this presentation. Okay, well, go and look it up on Wikipedia about work function. So that's one aspect, and then let's see if I've actually got that. Okay. So I want to come to what is kind of successful here. The starting point, I think, probably Iraj's claim that what is it? That inside the zeolite you've got a 3 billion volts per meter of electric field. It's like a static electric field as part of the way the atoms are arranged in the zeolite mesh. So high electric field with low work function compounds in there. So thinking about the Canon patent, and they've got maybe doped and they are receiving hydrogen species. Then you have patent of the recent Clean Planet patent, and again they are accelerating, putting electric field into a cathode, which is a hydrogen storage member that they're creating on the fly, and that might be doped as well. And so there's a lot of similarity between these things. And in an earlier presentation, I said that the 3 phases in a hot cat might be relevant. And I'm going to come on to why it's relevant. I also said publicly that in the ECAT-X, as I imagine it, but I don't know whether it is, that you had a capillary tube of sapphire. The capillary tube of sapphire would have a group 10, I said preferably platinum, but that was because of the temperature cited at the time. I think it's been cited slightly lower, so it could even be nickel. And around that nanostructure coated, or doesn't necessarily need to be, central electrode, and around the sapphire, you then have another coil electrode or plate electrode that is a discharge through the alumina. And this was basically immediate for me because it was building my understanding of what the process is. And so here is the big giveaway here. I don't know whether the couple of reinforcing things. One, and I must go in about 2 minutes, so I've got to wrap this up. One was the repeated repetition in the Clean Planet patent that the nanostructures themselves caused the electrons to form effectively a super electron, a heavy electron. And they go on and on and on and on about it. Well, without saying it, we've got muons observed in the work of Holmlid and Olofsson. And what is that? Well, they've got a potassium ion, so a transition metal and an alkaline earth metal in there. Are we just getting better at creating muons? Or is it a little bit further than that? And so my understanding of this, and the data points keep adding up, we might be creating muonium. And muonium is where you like have a mu plus and an electron, and it effectively forms an analog of light hydrogen, a proton and electron. And if I go to this, I don't know if you can see it, but from a 1970 Bulletin of Atomic Sciences, we've got Edward Teller and Lampf Meson Physics Laboratory. And they're saying that a new hydrogen chemistry, hydrogen-like chemistry, muonium chemistry, will be explained and exploited. This will entail the formation of large quantities of short-lived molecules, which can, I mean, muonium 1 second, or muons can live up to 1 second. They're actually incredibly long-lived as far as kind of particle lives go. Short-lived molecules which have much intrinsic interest and will contribute to understanding of classic chemical processes. The tantalizing questions involved in the interaction of mu mesons with electrons may see successful resolution within the next 10 to 15 years. I don't know whether it did. Anyway, it says here that these beams of mu mesons will permit detailed studies of mu meson catalysis of nuclear reactions, including fission and fusion processes. 1970. Okay, we got Edward Teller. Oh, yeah, excellent. Let's see if we can catalyze fusion with muonium. And then the last data point, second to the last data point, which was really exciting for me. I was researching this way back when, and before a lot of these interesting data points came in. You had this thing called some research done. It's done at I think it's done at Stanford. I need to look at it, but it's electric field induced muonium form fire. So essentially, this guy's J.D. Brewer et al. They took some sapphire, they put a high electric field across it, and they discovered that they got muonium coming out the other side. And also, they speculate that they got muonium minus, which is like protide. It's like a hydrogen molecule with 2 electrons, only it's muonium. It's muon with 2 electrons. Could this be one or the reason why we get LENR? Are we just getting better at forming muons? Muonium minus. If you imagine you've got muons being created between the high discharge on the outside of the sapphire tube into the center electrode. And charge is creating nanoparticles on that central electrode as it does it. You've got nanoparticles. If you've got it doped with some low work function material, you've got it donating electrons. So if it's muonium and it gets an extra electron, it's going to be even better at going into that transition metal. You can actually look at on Wikipedia, look at muonium, and you can see that within the top 2 lines it says, for atoms where muons have replaced 1 or more electrons, see muonic atom. Okay? So there you go. I didn't want someone else to capture this. I have to go now. There's a hell of a lot more on this. But you know, just a few weeks ago when I was going, really, is this something I should really be considering? I mean, does actually know what he's got? Does anyone know what they've got? And then there is a German a dielectric barrier discharge system, how I'm describing the ECAT-X to work, okay? And what are they using as their dielectric barrier? They're using aluminium oxide. I'll give some links to this recording, this video. I'll put the proper presentation when I get out, but I now have 25 minutes to get to the bus. So thank you for watching. Any questions, I'll be really happy to listen to people's questions. And I will post this video with some overlay graphics. I'll try and dump them on because I'm making a recording locally. Any questions, I'll try and answer them whilst I'm on the road. But essentially, I'll be looking at being better at creating muons, muonium and muonium minus. What is causing this effect? Thank you for watching.